Here so far is we have how some operations on functions affect graphs. We know that adding a number to the output value of a function shifts the graph in totally the intuitive way. Adding a number to the input of a function shifts the graph in exactly the opposite of the intuitive way. Multiplying the input or the output of a function by a negative sign affects the graph in kind of exactly the way that you would expect. So if we know what each of those things do, we should be able to understand what the sum total of the effect of a sequence of a bunch of these will have on the graph. Let's do that. So let's try to sketch the graph of this, negative x plus 3 quantity squared plus 4. All right, and I'll even suggest which steps to do. So for the graph of x squared, well, we know what the graph of x squared is, right? It's like an upward opening parabola. And happily, on this graph, I haven't indicated any hash marks. So I'm not worried about getting the right scale because I won't be able to get the right scale anyway. And there's no scale information given. So it looks something like that. If that's what the graph of x squared looks like, how do I get the graph of minus x squared? Yeah. Yeah, flip it down. Great. Do the flip that changes things vertically. Get the graph of minus x squared by flipping over the x-axis. And again, I'm not worried with getting the right scale, and in fact, you'll notice that that doesn't even look symmetrical like it should, but good enough for these purposes. It's not the worst attempt at the parabola I've drawn. From that, how would you get the graph of minus x plus 3 squared? Yeah, I see people just pointing at me. A shift left a total of 3. Shifting, left by 3. So it's there. Maybe I'll label it. That's 0, 3. Nope, 3, 0. And that's right, not left. It's going to be a day. It's been a long semester. Minus 3, 0. And if I want to add 4 to the whole function, I will shift it up by 4, I guess. Shifting up by 4. So that point minus 3, 0 will now be the point minus 3, 4. That might not look quite to scale, but I'm happy enough. Maybe I'll make sure of one other thing. I'll make sure I have the Y-intercept correct, at least up to whether it's positive or negative. How do you compute the Y-intercept? Plug in x equals 0. So let's plug in x equals 0. So I'll have minus, see, 0 plus 3 is 3 squared is 9. So minus 9 plus 4. Is that positive or negative? Negative. And that's all I'm going to be able to detect here. I'll have negative y-intercept, so it'll look something like that. Maybe I can even label it 0 minus 5. It didn't ask to do that, but it's nice to at least know whether you hit the axes and about the right places. That example feel pretty okay? So people notice I did this in a specific order. And there's a reason I did. So let's see what happens if we do it in a different order, see if we wind up with the right function. We won't, and then we'll talk about why you don't get the same function. So this won't be, I don't think I have space for this in the notes. No. So I'm going to do this on the board. what I'm about to do on the board will be incorrect, but I want to talk about why it's incorrect. So, let's do something similar. Right. There's x squared. Let's do all the same moves. Let's shift left by 3. Up by 2. And then flip over the y-axis and see if we get the same thing. The y-axis, x-axis.
It's supposed to be 4 too. Up 4.
Thank you. All right, so let's just see what happens. So you take this, you shift it left 3. So you end up with something like that. You then go up 4. You end up with something like that. You flip it over the x-axis. You end up with something like that. Is that the same as the thing that we just graphed? So somehow, like, order makes a difference. And let's actually see what we did graph. So if this is x squared and we shift left, then what have we just graphed? It'll be something squared. Yes. And then I shift up 4. What does that do to the function? Adds 4. And then we flip it over the x-axis. What does that do? A negative on the outside. So I should take the whole function and make it negative. And maybe expand that out a little bit. Is it now clear why that is a different function than we wanted to graph? So one way of being confident that you have the function you want is by writing out the individual steps and being very careful with all of your parentheses. The other thing to note is the order that you should deal with these things is first deal with the thing in front of the parentheses, then you can deal with the shift. And notice, if you go left and then up, as opposed to up and then left, does it make a difference? No, you'll get to the same spot. So those two you can do in either order. Just do them second. And then this x might have a negative sign in front of it. Deal with that last. So here are some examples that we might do. So here are 2 examples that might be worth graphing. Minus absolute x minus 3 plus 1 minus the square root of minus x plus 3 plus 1. Yeah.
Can you pull down the
Oh, yeah. That'd be good. So let's decide how we want to proceed. So the 2 things I could envision doing are I talk through one, then I let you guys do some of the other. I break you 2 into groups and have you do the 2. Would people like to see me go through one more example before I have you do an example? Okay. That is what we will do. So let's try to sketch the graph of minus absolute x minus 3 plus 1. So it looks like the elementary function to start with is just absolute value. Do you know what the graph of absolute value looks like? There's your starting point. Y equals absolute value of x. The graph looks something like that. And just like the previous example, first we'll deal with any negative sign outside of the parentheses, any negative sign that you hit the function with. Then we'll deal with shifts. Then we'll deal with any negative sign that's right next to the x. So what's the next function that I should try to graph in this sequence? Negative absolute x. What does that do to the graph? Flips it over the x-axis. And now we'll see what your preferences are. How many people would want to do the shifts in 2 separate steps, and how many would prefer to do them all at once? 2 separate steps? All at once? All right, I'll do it all at once. So let's at least write each one down. The minus 3 next to the x, that means I should shift to the right by 3. And the plus 1 means I should go up. So this point here, which is right now at 0, 0, we'll go right 3, up 1. So the graph of negative absolute x minus 3, close absolute value, plus 1. This point will go 1, 2, 3, up 1. And then it'll have that same absolute value-y looking shape. And let's label that. 3, 1. People feel pretty good? In fact, let's go ahead and do a single thing to check. It looks like the graph that I just generated goes to the point 3, 1. Let's take the formula for that function, plug in x equals 3. Do you get a total of 1? So, without even writing things down, see, plug in x equals 3. 3 minus 3 is 0. Absolute value of 0 is 0. Negative 0, still 0. Plus 1. Yeah, I landed at 1, so I'm confident enough. That procedure seemed pretty good. So here, I'll have you do this next one. Let's talk through the sequence of steps, though. So it looks like the elementary function to start with is the square root function. And then I see a negative in front of the square root. Negative square root x. Next, deal with the shifts. Negative square root x plus 3 plus 1. Then there's a negative sign in front of the x. Negative square root negative x plus 3 plus 1. And now I'll just be quiet for a bit. I mean, once you have a graph, unlike a quiz, I'm totally comfortable with you checking your answer for someone who happens to be like near you. Because some of you don't really have someone near you today. Oh, speaking of. Let's see. First things first. Pause the recording so I continue recording. All right. So, describe to me the graph that you wound up with. It looks like square rooty, right? But it has like an endpoint. Where's the address of the endpoint of this? 3, 1. Does that agree? Okay. And then, like, it's square rooty, so it either goes like up right, up left, down right, or down left. So something like this. Ish. Cool. People feel pretty okay about this? Nice. So, right, we have all of those things done in the order in which they interact. There are two more things that you could possibly do, right? You could like multiply the function by -1. Or surely you could multiply the function by 7 and it'll do something similar. And you can multiply the input x by a number as well. Let's just talk about those. And let's just talk about them via this example. So here we see the graph of a function. It has some formula there, but the exact formula doesn't matter. There's a formula for the function y equals f of x. There it is again. Here is what the graph of f of 2 times x looks like. There's what the graph of 2 times f of x looks like. And here's what I would like you to tell me. How do the graphs seem to be related? How does the red graph on the left compare with the green graph?
They're both triangles.
They're both triangles. So they both have the same type of structure. That's good. But they're not like the same triangle. How do they differ? How would you get one from the other? One has a wider angle. The angle has become smaller in the red one. Yeah.
Vertical and horizontal shifts? Or stretch and stretch?
Yeah. Or just this one. So vertical or horizontal? What's the difference?
Horizontal.
There's something horizontal and it looks like it's being squished. So, it looks like y equals f of 2x is horizontally compressed compared to y equals f of x. That seem believable? Let's look on the right. So if the thing on the left is a compression happening, what would you say is happening on the left to go from the green to the red?
Expansion?
It's expanding. Yeah, it's like getting taller. Things are stretching vertically. 2 times f of x, y equals, is vertically stretched compared to y equals f of x. And whenever I write the word stretched, it always looks wrong. Is that actually how you spell stretch?
Mm-hmm.
Okay. Like I'm never sure about that second T, or if there should be an A somewhere in there. All right, I'm happy. So let's just codify that. Let's put that into a statement. Sorry, was that too fast? Do people okay with me flipping? Okay, I can wait. Cool. So, here's the general principle. Let C be any positive constant. 5, 23, 6, doesn't matter. 0.5, anything positive. The graph of y equals c times f of x is given by, and I like this two ways, I think. Stretching vertically by a factor of c. That about agrees with what we did on the previous page. Maybe the factor of c is news, but it agrees with the previous page. The y values got doubled. You stretch by a factor of 2. And let's now write it in terms of that. Multiplying all y values by 2. And now when you write it that second way, that totally makes sense, right? 2 times f of x is the same as f of x, but all the outputs are multiplied by 2. Well, outputs are y values. So the graph should look exactly the same as the old graph, but all of the y values are multiplied by, oh, not 2. I don't know what the constant is. By whatever the constant c is. All right. And we saw what happened with f of 2 times x. The same thing, sort of thing happens for any constant. To get the graph of y equals f of c times x, you will instead compress horizontally by a factor of c. Said another way, all x values get divided by c. That makes sense? And it agrees with the previous page, I think. So let's make one remark about the order in which to do things. So again, if you do things in the wrong order, you'll get the graph of something different. And you'll see that you get something different if you keep track of what function you have at each stage and are very careful with parentheses. But in order to avoid this order of operations issue, deal with whatever is multiplied by the whole function first. Then, second, deal with whatever shifts you need to. And then finally, deal with whatever is multiplied by the x. That make sense? So let's see an example. Let's try to sketch the graph of negative 1/2 x minus 2 quantity squared plus 3. And I'll try to track, well, here I say where a few interesting points go. Maybe like there will be a Tony or roundy point, so we'll track that, because that's an interesting point. And then maybe we'll try to suss out any intercepts. All right, so let's go ahead and do it. Start with the graph of y equals x squared, I guess. So, according to the order of things listed above, what's the first ingredient I should deal with?
Negative.
Let's deal with the negative on the outside. What will that do to the graph? Sorry, say again, my boots were
Flip it
squeaky.
over the x-axis.
Yeah, we'll flip it. It'll be nice when it stops being cold out and I don't have to wear boots. I guess I could have an extra set of shoes. All right, what should we deal with next?
The -2 or the +3?
-2 or the +3. And since I only have 4 spaces, maybe I'll deal with
Yes,
both.
both.
So I'll do all of the shifting. So I'll try to get negative x minus 2 plus 3. So that will shift me how much in what direction? 2 to the left and 2 to the right.
Oh, 2 to the right.
Yeah, okay. You're good. 2 to the right. 3 up. So this 20 around you point, vortex we'll call it, is at the point 2, 3. And even though this isn't the final graph, maybe I'll make sure to have like the right y-intercept. So to find the y-intercept, plugins, oh, I lost the square. Negative 2 squared, so that's 4, negative 4 plus 3. So the y-intercept is negative 1. Graph looks something like that. And what's the last thing I need to deal with? The 1/2. So that'll be negative 1/2 x minus 2 squared plus 3. So what will that do to the graph?
Compress it.
In a sense. It will compress it by a factor of a half. And that's like a confusing thing to say. So let's read it the other way. All of the x values will get divided by 1/2. And let's write that out what that means, because it's going to do something. So the new x value is the same as the old x value divided by 1/2. But that's like an overly complicated way of writing something. What, dividing by 1/2 is the same as what? Multiplying by 2, right? Dividing by a fraction is the same as multiplying by the reciprocal. 2 times old x value. So all of the x values are actually getting doubled. So, like, we're compressing, but we're compressing by a factor of 1/2, which really means we're expanding by a factor of 2. So, let's do that. All of the x values are getting multiplied by 2. So this point right now, which is at 2, 3, what point is that going to go to when we make this transformation? 4, 3. The x value gets doubled. And there's no real scale information, so I'm not worried about doing it wrong. The intercept there at 0, -1, where will that go when I do this transformation? What happens to that when you double the x-coordinate? Nothing, right? Yeah. 0 times 2 is still 0. And maybe that looks a little bit sharper than you would like. 0, -1. Groovy. How do people feel? Does that seem pretty okay? Nice. So, given the example that we just completed, so we just sketched the graph of this function. Suppose you were given a multiple choice question in which you are asked which of the following might be the graph of that function we just graphed, and you were presented with these 3 examples. Which one of those, if any of them, would you report as being correct? Oh, maybe if they're multiple choice, it should be like lettered A, B, C. Are you on A? Is that consensus? All right, yeah, it's A, right? In fact, we tracked this point to be at 4, 3. That looks like the point at 4, 3. Y-intercept looks right. Yeah. Cool. People feel pretty comfortable right now? Nice. So I want to do a few more things, and let's maybe list the examples that are still in this packet. After this, we'll be done with this particular packet. On Monday, I'll have a new shiny packet to hand out for you. So, let's put a bunch of stuff together. Let's graph this piecewise function. The piecewise function, which is x minus 1 if x is less than 2, x minus 1 squared if x is between 2 and 2, including 2x and 3, and x equal to 3 if 3 is less than 2. So we had a strategy for graphing piecewise functions, right? Start by graphing each piece. Are each of those things that you know what their graph should look like? Yeah. So I guess starting point is let's graph each piece, and maybe I'll even see what people would prefer. If people want me to talk through, or would people like time to do stuff on their own and then we come together? People want me to talk? Okay, at least a few hands. Let's graph each piece. The graph y equals x minus 1, what does that graph look like? It's a line. Slope is, y-intercept is. So, color code, it looks something like that. And maybe we'll even like go ahead and highlight where I care about that function. What inputs do I care about for that function? X is less than 2. So, I don't know. If about there is x, oh, x is less than 2, not negative 2. If like there is 2, there's the piece of the function I care about. Should I have an open circle or a closed circle at the end? Open. And let's go ahead and like make sure that point itself is correct. That's the point 2 comma what? What's the y value? 1. All right, plug in 2, you get a y value of 1. Cool. y equals x plus 1 squared. All right, so maybe it's like a single shift, so we'll try to do it like this one. So you would graph that by starting with the parabola, the y equals x squared picture, and then you would shift it how much in what direction? 1 to the right. Awesome. So it'll look parabola-y. It'll still open up. There's this point at 1, 0. We'll do something like that. What points on, what inputs do I care about for that graph? What x values? 2 to 3. So let's see, I guess that's like there to there. Should one of those have an open circle at the end? The one at x equals 3, so. Oh, I'm doing the wrong color coding. I didn't tell you what the right color coding is, so I guess it doesn't matter that much. So solid endpoint there, open circle there. I'm going to try to have all the actual pieces of graph I care about in red, not for any particular reason. Let's get the right endpoints. So this endpoint is at the coordinate 2, comma, what y value do you get when you plug in 2? A euro 1? Does that agree? Nice. How about that endpoint? That endpoint is at x equals 3, and what y value? Yeah, that's right. Okay. And finally, the graph of y equals 3. What does the graph of y equals 3 look like?
Straight line.
Straight line. In fact, a horizontal line. Slope is 0. Y-intercept is 3. This one will be other blue. And I care about that graph from x equals 3 onward. With a solid dot at the end, because I want to include, so that's the point x equals 3, and what y value? What is the y? 3, all right, the y is always 3. All right, so we have each piece. Let's put them together, doing exactly what we know. So I'll copy this point. So here's the point. Two, comma, 1. Then the graph will come down this way. Then I see coming from the parabola, I have that bit going from 2, 1. Oh, cool. So that'll actually fill in that open circle that I just drew, right? Then it'll curve upward until it gets to the point 3, 4. And then a solid dot at 3, 3. And an arrow going right. Does that feel pretty okay? So you can put together all of the things that we've done with ideas like piecewise functions. So the two things in the note packet yet are one more example of doing this with a piecewise function. And then an example in which I say, here's the graph of a function, sketch the graph of this function. And, well, we'll just see what people like. Do people want to spend time graphing another piecewise function, or do people feel good? People want to spend time on another piecewise? Okay. I see one hand up, but only one hand. So maybe I'll delay, and we'll hit it at the end. After we hit this other example where we think about, if you know what the graph of a function looks like, how do you get the graph of a transformation? So let's look at this graph on the next page. Well, unless you have like a particular question about what just happened? Oh, okay. So, here is the graph of a function. So here is the graph of y equals f of x. Go ahead even and advertise some endpoints. endpoints, points where something interesting happens. -2, 1, -1, 0, 0, 1, 1, -1, 2, -1. So here's the graph of a function. Let's try to sketch the graph of -2 times f of 1/2 x plus 1 minus 1. And let's just go ahead and do it. So there's an order in which we should deal with these things. So what's the first one of those ingredients that I should deal with? The negative on the outside. In fact, would you feel comfortable dealing with the whole -2 at once? Yeah, right, so that'll flip it, but then also stretch it. And it doesn't matter if you flip then stretch or stretch then flip. Those will both do the same. So let's deal with the -2 first. And what bit should I deal with next?
To the left one and up or down one.
Yeah. Deal with these second. And then finally that x equals, that 1/2 next to the x. Groovy. So, let's try to do it. So that -2 next to the f. So first let's graph y equals -2 times f of x.
That's normal.
Oh, I was going to say that. Who am I to judge? What will that -2 do to the graph of the function?
Multiplying all the y values by 2.
All the y values will get multiplied by 2. So let's just track each and every one of these points. And I guess the first one I'm going to do in baby blue. So this point at 2, -1. Oh, well, you can see it on your paper, even if it's not on mine. This point at 2, -1. What point will that go to after we do this transformation? Right now it's at 2, -1. Y value gets multiplied by -2. What's -1 times -2? 2. You were looking at me like I was an idiot because I was doing something dumb, right? That's not the point 2, -1. What point is that?
-1.
-2, +1. Great. It's written right further up. Not that that helps. All right, -2, +1. When I multiply that y value by -2, what y value do I have? -2. So the new point will be -2, -2. Cool. -2, -2. Nice. The next point I see is the point -1, 0. Where will that go when I multiply the y values by -2? Awesome. This next point appears to be the point 0, 1. What will happen to that point? 0, -2. This next point is at 1, -1. So that will go to the point 1, 2. This point at 2, 1 will be 2 minus 1. Will become 2, 2. It'll look nice and linear between. So are we just completely done and that's the final answer? No, that's like one of the 3 things we need to do. What's the next thing that we should do?
Move it to the left one and down.
The left one down one. So that'll give me y equals -2 times f of x plus 1 minus 1. So go left 1, down 1. All right, so that means, well, we can just kind of draw the picture of what happens when we go left 1, down 1, right? Each one of those points will go left 1, down 1.
I think you went right.
Of course I did.
That's like
All right. Now it's correctly gone left 1 and down 1, all right? Okay. Left 1, down 1. Left 1, down 1. Left 1, down 1. All right. And it's a good illustration that it's easy to make mistakes, and so important when you're done with these processes to have something in mind to check your answers. So we'll continue the process. I think we'll have enough time to check it at the end too. What's the last thing I need to do?
1/2.
The 1/2. So what will that do?
Multiply x values by 2.
Multiply x values by 2. Y equals negative 2f of 1/2 x plus 1 minus 1. And maybe I'll write that in the obtuse way and then the correct way. So x values divided by 2, but that means the same thing as x values will get multiplied by 2.
Divided by 1/2.
Thank you. It's been quite a week. I'm glad some of us are able to keep things straight. So it looks like this point right now is at 1, 2, 3, so negative 3 by 1, 2, 3, negative 3, negative 3. So where will that point go when I double all the x values? So right now it's at
Negative 6.
negative 6, negative 3. So this will now be another 3 over this way. Well, it's unfortunate the way that I wrote, but that's okay. Negative 6, negative 3. This point, where will it go when I multiply all the x values by 2? I guess right now that's 2, so it'll go there. So we'll see this. This point will wind up here. Where will that point that is on the y-axis go when I multiply all the x values by 2? Will it go anywhere? Yeah, it'll stay put, right? Anything on the axis stays in the same place. And finally, there. So there is our final graph. And as was observed, that's a lot of steps. And you guys caught me doing something wrong at least twice. But sometimes you let me get away with doing things wrong and you don't catch me. So what's something we could do to check if this graph is correct?
Plug in values.
Plug in values. So I know, for example, we know it's useful. It looks like x equals 0, y equals 1 should be on the graph. So let's do a quick check. So let's take the formula that we have right here, plug in x equals 0, see if it goes through the right point. We'll get negative 2 times the function evaluated at, and then, you know what, I have colors, so let's do colors. 1/2 times 0 plus 1 minus 1. All right, so let's start with the stuff inside the parentheses. What's 1/2 times 0 plus 1?
1.
Just 1. So this is negative 2 times f of 1 minus 1. And do we have the graph of f somewhere on the paper? So look at the original graph of f. What does the original graph of f tell you that f of 1 should be? Yes, perfect. -2 times f of 1 is 1. F of 1 is -1. -1. Does that, well, let's just keep on computing. -2 times -1 is 2, -1 is 1. Does that agree with the point that we found? All right, so I'm reasonably confident. I guess if I wanted to be 100% confident, I'd check like 1, 2, 3, 4, 5 points. And then I'd be absolutely sure, because it's straight lines between everything, and all these transformations send straight lines to straight lines. Neato. People feel pretty good with this idea? Yes. So all of the extra credit for the semester is due by the time that I go home on the last day of class before our final. That being said, on none of the extra credits do I, you'll have it in there and you'll come home and you'll present it. You won't hand in anything. If I decide I'm happy, everything's perfect, you'll get 100% on the extra credit, but it's not my intention that that ever happens. I'll say, well, like, that negative sign should probably not be a negative sign or something. And so I'll say, well, as a consequence, this is like good for 50%. And I'll give everything back to you. You'll leave. You'll come back the next day with that issue corrected. And then you'll get it. But if you wait till the last day to do that, then maybe you don't get an extra day to do it. So come in sooner or later.
And question, I have some issues with the camera. Would it be okay if I turned in my open-ended work to do tomorrow as
Then Horley. Oh, there's your name right there. Okay, so here's what I'm going to do.